Given quality and minimum wage arrays for n workers, and an integer k, hire exactly k workers as one paid group. Each hired worker must receive at least their minimum wage, and every pay in the group must scale with quality the same way. The goal is the smallest total cost for such a group. Example 1, quality 10-25, wage 70-50-30, k equals 2. With 3 workers we only have 3 pairs to try. Workers 0 and 1, cap ratio 7, 7 times 30 equals 210. Workers 1 and 2, cap ratio 6, 6 times 25 equals 150. Workers 0 and 2, cap ratio 7, 7 times 15 equals 105, the cheapest group. The output is 105. Example 2, 5 workers, k equals 3. The cheapest valid trio pays 4 to workers 0 and about 13.33 to workers 2 and 3. Total cost is about 30.67. This problem gives us 2 conflicting rules. First, we must pay workers in strict proportion to their quality. Second, nobody can be paid less than their own minimum wage. If we try to be cheap and pay our high-quality worker their bare minimum, the shared ratio forces our lower-quality workers' wage into the floor, breaking their minimum wage. We need one unified metric to balance this scale. To unify these rules, we divide each worker's minimum wage by their quality. This unlocks a single, crucial metric, their minimum cost per unit of quality. Worker A demands $2 for every point of quality they bring. Worker B is remarkably cheap, asking only 25 cents per unit of quality. This ratio changes everything. Here is the core insight. When we hire a team of workers, the entire team must be paid using the exact same unit rate. So who sets that rate? The worker with the highest ratio in the group becomes the captain. If we instead pick a captain with a lower ratio, like 1.5, anyone demanding a higher rate, such as worker A at 2.0, is immediately underpaid, breaking the rules. The captain's ratio is the master multiplier for the whole team. Once we understand the captain's rule, the total team cost becomes beautifully simple. Instead of adding up each salary on its own, we factor out the shared rate. The total cost of any valid team is just the captain's ratio multiplied by the sum of everyone's quality. To minimize the total, we must shrink both of these factors at the same time. To systematically find our best team, we sort the entire candidate pool by their ratios, from lowest to highest. Then we walk from left to right. Whoever our right boundary lands on automatically becomes the captain, setting the master rate. Everyone to their left is guaranteed to be a legal teammate, because their lower ratio demands are safely covered by the captain's higher rate. Here is a natural question: since ratios get more expensive as we move right, why not just take the first few workers and stop? Here is the trade-off. A cheap ratio worker can carry a massive, anchor weight quality that inflates our total sum. By sliding our window to the right, we accept a slightly higher captain ratio in exchange for the chance to find ultra-low quality workers that drop our total team weight dramatically. As we march forward, expanding our pool of valid candidates, our team size will eventually exceed our target size, K. Remember our formula, cost equals ratio times total quality. Since the captain's ratio is locked for this step, the only way to drop the cost is to aggressively purge quality. We use a max heap to instantly eject the worker with the highest quality, greedily keeping our total team quality as small and inexpensive as possible. We kick off our solution engine with structural packaging. We loop through the inputs, binding each worker's wage and quality into a single profile, while computing their exact cost per unit of quality. Then we sort the entire pool in ascending order by this ratio, locking our candidate timeline from the cheapest unit rate to the most expensive. With our workers prepared, we initialize the core state monitors. We spin up an empty max heap dedicated to tracking worker quality. We zero out the total team quality counter, and we set our minimum cost target to infinity, giving us a ceiling to beat. We launch our primary sweep across the sorted candidate line. Whichever worker our loop lands on instantly becomes our active captain, setting the master ratio for this step. We take that worker's raw quality score, insert it directly into our quality heap, and add it to our running total quality ledger. The heap just reached size K, so this is our first complete team. We cost it as the total quality, 25, times the captain's ratio of 6, which is 150. That beats infinity, so it becomes our best cost so far. As we keep ingesting candidates, our heap eventually breaches the target team size of K. The moment we hold K plus 1 workers, we are oversaturated. Because the captain's ratio is locked for this step, we immediately dump quality to save cost. We pop the largest quality value off the top of the heap, discarding that heavy anchor and subtracting it from our running sum. Once our quality heap holds exactly K elements, we have formed a legally valid team under the captain's rule. We multiply our consolidated team quality sum by the captain's active unit ratio to calculate our current runtime expense. We compare this against our global minimum cost target, greedily capturing and locking down the lowest value ever recorded. Our engine completes its linear scan across the remaining workers, evaluating every possible captain option while keeping the leanest quality pool inside the heap. Once the loop runs out of candidates, the search space terminates. We harvest our optimized minimal value from the tracking board, returning our definitive, absolute minimum cost to hire our team. Time is n log n, sorting the workers by their ratio is the dominant cost. The sweep that follows pushes and pops each quality once from a heap of size at most K, which is n log K, a little cheaper. Space is order n, we keep the sorted list of workers, plus a heap that never grows beyond K qualities. We define our routine, given each worker's quality and minimum wage, and the team size K. We start with an empty list of worker profiles. We loop over every worker. For each one we compute the cost per unit of quality, the wage divided by the quality. We store that ratio together with the worker's quality. Then we sort all workers from the cheapest unit rate to the most expensive. We create an empty max heap to hold the qualities of the current team. The running total of team quality starts at 0. And the best cost so far starts at infinity. Now we sweep the sorted workers, one captain at a time. We push the current worker's quality onto the heap. And add that quality to the running total. If the heap now holds more than K workers, we pop off the largest quality and subtract it, keeping the team lean. Whenever the heap holds exactly K workers, we cost this team as total quality times the captain's ratio, and keep the smallest cost seen. After the sweep, we return that minimum cost.